Picture this. It's June 6, 1989. You are tracking this massive NASA stratospheric balloon that just launched out of Palestine, Texas.
Right down in Texas.
Yeah, and it's currently flying at like 120,000 feet, drifting peacefully high above this really violent thunderstorm near Graham. And then, completely out of nowhere, there is an uncommanded payload release.
The balloon just suddenly drops its cargo.
Exactly, just drops it. And for months, investigators are totally scratching their heads. I mean, they review every single piece of telemetry, looking for, a mechanical failure or a software glitch, anything.
And they find absolutely nothing normal.
Right. Finally, they point the finger at a culprit that, at the time, seemed physically impossible. They blamed a quote-unquote bolt of lightning traveling upward from the clouds and striking the balloon from below.
Which completely subverts our basic, everyday understanding of how the world operates.
Yeah.
I mean, we are taught from childhood that gravity pulls things down and lightning strikes the ground.
Yeah, the sky creates the danger, and the Earth just receives it.
Exactly. It's supposed to be this binary system. But when you step into the upper atmosphere, suddenly all those rules just get thrown out the window.
It's wild. We're looking at an electrical landscape that is completely alien to what we experience down here on the surface. So today's deep dive is all about phenomena called sprites, specifically red sprites.
And we are pulling from a pretty extensive stack of scientific documentation, research papers, and historical logs for this.
We really are. We're going to explore these massive, elusive electrical discharges that happen 31 to 56 miles above thunderstorm clouds.
So we're talking 50 to 90 kilometers straight up in a region called the mesosphere.
Right. And, when you look out the window at a rolling thunderstorm, you naturally assume all the action is happening right there, between the dark clouds and the dirt.
That's where the noise is, anyway.
Yeah. But we're going to explore this secret, mostly silent light show happening at the very edge of space. It's like this unseen ecosystem of electricity above our heads.
And the timing of that NASA balloon accident is actually one of the great ironies in atmospheric science.
Oh, because they didn't even have a name for it yet, right?
Exactly. It happened in early June of 1989, but the phenomenon they ultimately blamed the accident on didn't have a formal name. They had to retroactively assign the blame to a spite, because that specific term wasn't actually coined by researchers until late 1993.
That is incredible. And just 1 month after NASA lost its payload over Texas, a completely accidental discovery would finally pull back the curtain on what was actually happening up there.
The timeline of the discovery is super fascinating, because the phenomenon wasn't entirely new. It was just unproven.
People had seen it before.
Oh, yeah. You can trace sporadic reports of these events going back well over a century. The earliest known recorded sighting in the literature was actually documented by Toynbee and Mackenzie in 1886.
Wait, 1886? So you have people in the 19th century, maybe like sailors on the night watch or early weather observers, just seeing giant red flashes high above the clouds.
Yeah, and jotting them down in logbooks.
I can only imagine how hard it was to convince people they weren't just seeing things.
Oh, the skepticism was intense. But the idea slowly gained theoretical traction. By 1925, you have the Nobel laureate C.T.R. Wilson looking at the physics of storms.
Right, doing the math on it.
Exactly. On purely theoretical grounds, without any photographic evidence, he suggested that electrical breakdowns could and should occur in the upper atmosphere above powerful storms.
Did he ever actually see one himself?
He did. He even witnessed a flash in 1956 that he believed was one of these upper atmospheric events. But for the longest time, it remained entirely theoretical and, anecdotal.
Until the summer of 1989, scientists from the University of Minnesota were out testing a low-light video camera. And looking for sprites wasn't even the primary goal of their mission.
No, it was a total accident.
But they accidentally captured the very first image of one. Now, if you look at the historical records we pulled for this deep dive, there is a funny little discrepancy.
Oh, with the dates.
Yeah. Some summaries list the date of this first photograph as July 4th, 1989, while deeper history sections note it as July 6th.
It's a slight quirk of historical record keeping. But whether the camera was rolling on the 4th of July or 2 days later, the impact of that footage was just monumental.
Who actually captured it?
It was captured by R.C. Franz, R.J. Nemsek, and J.R. Winkler. They published it in the journal Science in 1990. By aiming this highly sensitive low-light television camera at the night sky, they finally documented a large upward electrical discharge.
And that single frame of video forced a complete rewrite of atmospheric physics.
It really did.
But I have to pause here and ask about that massive gap in the timeline. I mean, if people like Toynbee and Mackenzie were documenting sightings in 1886, why did it take over 100 years to just get a photograph?
Wow.
Were scientists just actively ignoring the reports, like writing them off as pilot hallucinations?
Not exactly. You have to consider the severe limitations of legacy technology. Capturing a sprite requires an incredibly specific and difficult set of observational conditions.
Because they're so fast.
Right. These events happen in a tiny fraction of a second. Furthermore, they occur high above thick storm clouds, which naturally block the view from the ground directly underneath them.
Oh, so the storm itself gets in the way.
Exactly. And if you point a standard film camera at a dark sky, the emulsion simply isn't sensitive enough to pick up the faint optical emissions of a sprite, not without leaving the shutter open so long that regular lightning just washes out the whole frame.
So it wasn't a lack of curiosity, it was a lack of night vision.
Pretty much.
You basically needed military-grade or highly specialized low-light video to see them clearly in real time.
The technology had to catch up to the theory. Until we had those specialized low-light video rigs in the late 80s, proving their existence with hard evidence was nearly impossible.
That makes a lot of sense.
And because they are so transient and incredibly elusive, several years after that 1989 video capture, they were officially named Sprites, which is a nod to the mythological air spirits found in folklore.
Air spirits, it's such a fantastic name. But once scientists finally had a sprite on camera, they had to figure out what they were actually looking at, right?
Yes, because it wasn't what anyone expected.
Right, because if you expect it to look like a giant lightning bolt shooting into space, the data would make absolutely zero sense. They quickly realized this wasn't normal lightning at all.
Far from it. Normal tropospheric lightning, the kind that strikes a tree outside your house, is a channel of superheated plasma. It's incredibly hot and destructive.
The sprites are different.
Sprites operate under completely different physical mechanics.
Let's break down the anatomy of a sprite because the visual scale here is just staggering. In 1999, a researcher named Roger categorized them into three main types based on their shapes.
And the shapes are pretty wild.
Yeah. First, you have the jellyfish sprite. And when we say jellyfish, we mean a glowing structure up to 50 by 50 kilometers in size.
Yes, kilometers.
That is a 31 by 31 mile electrical jellyfish hovering in space.
The scale really defines human intuition. You could fit entire metropolitan cities inside the bell of one of those jellyfish.
Then you have the column sprite, often called a sea sprite, which looks like a massive vertical pillar of light. And finally, the carrot sprite.
The carrot sprite is essentially a column, but with these long, root-like tendrils hanging down from it.
The colors are stunning too, right? The upper regions are this deep reddish-orange, transitioning into pale bluish hanging tendrils at the bottom.
Yeah, the color gradient is beautiful. But understanding the architecture of those shapes and colors requires looking at the invisible forces driving them.
Okay, lay it on me.
So sprites don't just happen on their own. They occur in direct response to the electric field generated by lightning flashes in the thunderstorms far below them.
The storm is the engine.
Exactly. Specifically, the process usually kicks off with a large, powerful, positive lightning strike from the cloud down to the ground.
Let's clarify that for everyone listening. Usually, normal lightning carries a negative charge down to the earth.
That's right.
A positive strike is much rarer. It makes up only a small percentage of lightning, but it's vastly more powerful, isn't it?
The energy transfer in a positive strike is immense. When that massive positive charge empties into the ground, it suddenly leaves the top of the thundercloud with a strongly negative net charge.
Okay, follow so far.
This sudden violent electrical imbalance can be modeled as a quasi-static electric dipole.
Whoa, hold on. Quasi-static electric dipole. Let's translate that into plain English for a second.
Sure.
Are you basically saying the storm system temporarily turns into a giant unbalanced battery?
The battery analogy works really well here. A dipole is simply two equal and opposite electrical charges separated by a distance.
Like the plus and minus on a Duracell?
Precisely.
Yeah.
In this case, the highly negative top of the storm cloud is one end of the battery, and the relatively positive region of the upper atmosphere, the ionosphere, is the other.
Wow.
For a tiny window of time, usually less than 10 milliseconds, a tremendously strong electric field is generated between those 2 points, stretching miles up through the mesosphere.
Okay, so you have this intense electrical tension pulling at the sky. But how does that tension turn into a 30-mile-wide glowing jellyfish?
It all comes down to atmospheric pressure. Because this tension is pulling through the upper mesosphere, which is about 50 miles high, The air pressure is incredibly thin.
There's barely any air up there.
Right. And in low-pressure environments, the breakdown voltage, which is the minimum amount of voltage needed to turn a gas from an insulator into a conductor, is drastically reduced.
Okay, so it takes less effort to make a spark.
Exactly. The electrical tension from our giant storm battery overwhelms the thin air, causing an electron avalanche.
An electron avalanche. Sounds like a sci-fi movie.
Electrons are stripped away and violently crash into air molecules, creating this massive chain reaction of light and energy.
So because of the low pressure up there, the energy doesn't need to tightly focus into a scorching, superheated lightning bolt to travel. It just kind of spreads out.
It does. It diffuses.
It's less like a lightning strike and more like a 30-mile-wide fluorescent tube suddenly turning on. It's cold plasma.
That's exactly it. The physics mirror a fluorescent tube perfectly. Calling them upper atmospheric lightning is actually a common misnomer because they lack those super hot channel temperatures.
They don't burn things.
No. They are wide, diffuse discharges of cold plasma.
And what about the red color? Why is it red on top and blue on the bottom?
The distinct reddish-orange glow comes from the excitation of nitrogen gas in that specific low-pressure environment.
Nitrogen, okay.
Yeah. Down near the surface of the Earth, if you electrically excite the air, the heavy concentration of oxygen quenches the reaction very quickly.
Because there's so much oxygen down here.
Right. But up in the mesosphere, the atmospheric pressure is so low that the quenching effect of atomic oxygen happens much faster than that of nitrogen.
So the nitrogen gets to shine.
Exactly. The nitrogen emissions are allowed to dominate the visual spectrum.
So the red color is literally just the nitrogen gas lighting up, exactly the way neon gas lights up in a neon sign.
It really is.
It's just a 30-mile-wide nitrogen sign flashing over the Earth. But, even understanding that these are glowing clouds of cold plasma, their sheer speed is baffling.
Yeah, it's incredibly fast.
And it's something scientists only managed to truly decode within the last few years, right?
Yes. Our understanding leaped forward again as camera technology evolved. For decades, the video frames we captured just showed these solid, glowing shapes.
Just big red blobs.
Right. But in 2019, a major revelation occurred. A team of researchers, Thomas Ashcraft, Jacob L. Harley, Matthew G. McHarg, and Hans Nielsen, managed to capture a sprite on high-speed video.
How high speed are we talking?
Approximately 100,000 frames per second.
100,000 frames per second. That is the kind of speed used to film bullets moving in slow motion.
It's extreme slow motion. And what they saw completely shattered the illusion of a solid jellyfish.
What was it, actually?
The footage revealed that sprites aren't solid geometric shapes at all. They're actually dynamic clusters of small balls of ionization.
The little balls of light.
Yes. The researchers measured these balls at the decameter scale, meaning they are somewhere between 10 and 100 meters across.
So roughly 33 to 328 feet across. Hundreds of glowing plasma spheres, basically the size of office buildings.
Exactly. And they aren't just hovering there either. They are launched at an altitude of about 50 miles, and then they streak downward.
And the data shows they move at up to 10% the speed of light.
Which is mind-blowing. The initial downward movement of these streamer balls is then followed, just a few milliseconds later, by a separate set of upward-moving balls of ionization.
Wait, I have to stop you here and push back on the timeline a bit. The physics of this are hurting my brain.
It's a lot to visualize.
The storm is on the ground. The sprite is 50 miles up in space. If the entire event only lasts a few milliseconds, and all these parts are moving at 10% the speed of light, how does a physical lightning strike on the ground trigger a plasma explosion 50 miles away almost instantaneously?
That's a great question.
Does the lightning itself travel up that fast? Is there a delay?
So the lightning bolt itself doesn't travel up. What is traveling is the electric field.
Ah, okay.
When the positive strike hits the Earth, the shift in the electromagnetic field propagates upward at the speed of light.
The speed of light.
Right. So the delay between the ground strike and the sprite forming is incredibly brief, typically just a few milliseconds.
Wow.
The tension snaps almost instantly. On rare occasions, that delay might stretch up to 100 milliseconds, but we are still talking about a tenth of a second.
It's nothing. To the human eye, the ground strike and the sprite would appear completely simultaneous.
Exactly.
That is staggering. The electromagnetic ghost of the lightning strike reaches space before the thunder even echoes.
And those descending streamer balls aren't even the very first thing to appear. If you look at the timeline, about 1 millisecond before the sprite itself fully forms, the sky often lights up with a halo.
A halo, like a warning flash.
You call it a precursor. The sprite halo is this pancake-shaped region of weak, transient optical emission.
How big is the pancake? It's enormous, measuring approximately 50 kilometers across and 10 kilometers thick, centered at an altitude of about 70 kilometers.
So the halo is almost like the flash of a camera bulb right before the actual picture is taken. It's this broad, weaker burst of energy that sets the stage in the mesosphere before the intense streamer balls form the actual sprite.
That's a perfect way to put it. The mechanisms are deeply linked. Research carried out at Stanford University in 2000 indicated that these halos are produced by the exact same physical process that produces the sprites.
The electric dipole thing.
Yes, the electric field causes an electron avalanche, but with a halo, the ionization is simply too weak to cross the threshold required to form those individual streaming balls of plasma.
It's like a sprite that just couldn't quite get the engine turning over.
Exactly. The Stanford research also yielded another surprise, actually.
Oh.
While full, structured sprites are highly associated with positive lightning strikes, sprite halos are actually not unusual in association with normal, negative lightning discharges.
Oh, wow. So they happen with regular lightning, too.
Yeah.
Yes. And because of their visual similarity, their flat shape, and incredibly short duration, halos are sometimes mistaken by observers for another entirely separate upper atmospheric phenomenon called LLVs.
ELVs. We have sprites, we have elves. I mean, atmospheric physicists clearly have a sense of humor about all this.
They definitely do.
But here's what really gets me. Even with high-speed cameras shooting at 100,000 frames per second and perfectly mapped physics detailing electron avalanches and quasi-static dipoles, these phenomena still refuse to give up all their secrets.
Oh, the gaps in our knowledge are still really significant. Despite being recorded in photographs and videos for more than 30 years now, a NASA Astronomy Picture of the Day blog explicitly states that the actual root cause of sprite lightning remains unknown.
So we know how they form. The electric dipole, the low atmospheric pressure, the nitrogen excitation, but we don't know the exact spark that decides why one forms over a specific storm and not another.
Right. The association with positive cloud-to-ground lightning is clear. But NASA notes that not all storms that produce powerful positive lightning exhibit sprite lightning.
There's a missing ingredient.
There has to be a missing variable in the equation. Some other condition or trigger must be present that we haven't fully identified yet.
So what could that missing variable be? Are meteorologists looking at, the physical shape of the anvil cloud? Or maybe minute temperature changes up in the mesosphere?
Researchers are looking at all of those variables. It could be localized gravity waves in the upper atmosphere, variations in meteor dust seeding the mesosphere, or highly specific geometries of the storm below.
Meteor dust. That is so cool.
It is. And the complexity deepens when you look outside of typical continental thunderstorms. For instance, in 2016, sprites were observed during Hurricane Matthew as it passed through the Caribbean.
Which is strange because a hurricane operates completely differently than a supercell thunderstorm over the plains of Texas.
Entirely differently. The role of sprites in tropical cyclones is presently unknown. The internal dynamics of a hurricane are incredibly complex.
So they don't even know what triggered it there.
No. Furthermore, research published in 2004 by scientists from Tohoku University found very low-frequency emissions, specifically VLF or ELF spherics, occurring at the exact same time as the sprite.
Let's define that. VLF and ELF spherics. We are talking about very low frequency and extremely low frequency radio waves, right?
Yes, these are broadband electromagnetic impulses. The Tohoku University data indicates that a massive electrical discharge within the cloud itself, rather than from the cloud to the ground, might be generating the electric field required for some of these sprites.
So the storm cloud is just humming with these extremely low frequency radio waves, discharging internally and shooting giant plasma jellyfish into space.
That's what the data suggests in some cases.
The whole thing just feels like it belongs in a science fiction movie, and the best part is that ordinary people can actually help solve these lingering mysteries today.
They can. The scientific community relies heavily on ground-level observations. In 2022, NASA launched a citizen science website and database called Spritacular.
Spritacular. The naming conventions in this field are just undefeated.
They really are. The goal of Spritacular is to collect, catalog, and study images of sprites taken by citizens around the world.
Because professional observatories can't be everywhere at once.
Exactly. Because these events can appear anywhere. There are large thunderstorm systems, Having thousands of camera lenses pointed at the sky globally is invaluable.
Where have they been seen so far?
Sprites have been documented over North America, Central and South America, Europe, Central Africa, Australia, and the Sea of Japan.
Basically everywhere. If you are listening to this deep dive right now and you want to try and catch a sprite yourself tonight, let me give you the recipe.
It's definitely something you can try.
It is difficult, but it is entirely possible. You need a highly specific setup, though. First, you need a powerful thunderstorm, one that is violently throwing off a lot of positive lightning. But here's the catch. You cannot be underneath it. You need to be far away, between 150 and 500 kilometers away, which is roughly 93 to 311 miles.
Distance is the most crucial factor. If you are directly underneath the storm, or even too close to it, the massive anvil clouds block your view of the mesosphere entirely.
You just see gray clouds.
Exactly. You need to be looking at the storm from a distance over the horizon, providing a clear line of sight to the starry air high above the weather system.
You also need a pitch-black, unlit sky. Any urban light pollution is going to completely wash out that faint red nitrogen glow.
It's very faint to the naked eye.
Yeah. You'll want red-sensitive recording equipment too, perhaps a modified DSLR camera with the IR filter removed, or a specialized low-light video rig.
And above all else, you need patience and luck.
So much luck. You are trying to catch a split-second flash of a 30-mile-wide air spirit that appears and vanishes in the literal blink of an eye.
The sheer elusiveness of sprites is what makes them so important to our broader understanding of the planet, though.
How so?
Well, for the longest time, science viewed the atmosphere in isolated, distinct layers. We studied the weather systems down in the troposphere, and we studied the radiation in the ionosphere out at the edge of space. But we didn't fully appreciate how electrically connected those layers are.
We really live our entire lives walking on the surface, looking up at the clouds. And for the vast majority of human history, we simply didn't notice that massive, glowing, red plasma jellyfish are flashing high in the Earth's atmosphere constantly.
They're happening all the time.
They are dancing over the Alps, they are flickering over the Caribbean Sea, they are illuminating the sky over Central Africa. These colossal structures of cold plasma appearing for just a few milliseconds at a time.
They perfectly illustrate how much of our own world remains unseen, humming just beyond the limits of human perception.
It's humbling.
It is a brilliant reminder that groundbreaking scientific discovery doesn't always require looking further out into the deep cosmos. Sometimes it just requires looking slightly differently at the sky right above our own heads.
And if you take that thought a step further, the implications are mind-bending. I mean, if our relatively calm, life-sustaining atmosphere here on Earth is capable of producing 30-mile-wide glowing red jellyfish, imagine the terrifying continent-sized air spirits that must be dancing in the crushing violent storms of a gas giant like Jupiter.
That is a terrifying thought.
Right. An entire universe might be filled with these invisible electrical ecosystems just flashing in the dark. So the next time you are out on a dark summer night and you see a distant thunderstorm rumbling way out on the horizon, don't just look at the lightning hitting the dirt. Look higher. Think about the silent, cold plasma ecosystem flickering in the black sky miles above it, completely out of sight.